Okay, so in this video, we're going to go over a bunch of descriptive statistics that you're going to come across quite a lot in your study of statistics. So we're just going to cover a lot of terms and make some distinctions in this video. First major distinction I want to make here is the concepts of a population versus a sample. Sampling is really kind of the core of what statistics is. You use a sample to predict traits about a population. So for instance, if you were interested in understanding what the average height of people in America is, you're not going to be able to measure the height of every single person in America. So you're going to take a sampling. And maybe you would stand around in Times Square and try to measure people's height. And based on taking 1,000 measurements, you would look at your averages for men and women and say, okay, this is based on what I've observed in Times Square, which is I don't know, maybe a fairly representative sampling of the U.S. population. I'm going to predict that the average height of men and women in the entire U.S. population is going to be pretty close to what I observed in Times Square. Another example could be, let's say you're interested in registered voters because you are doing a political survey and you want to figure out who's going to win the next election. What you might do is you might start randomly calling people, asking them if they are registered voters, and then asking them questions about their political preferences. In that case, what you're going to get is a sample that is representative of not the entire U.S. population, but the population of registered voters in the U.S. And so this is the key. You're never going to know the preferences of all the registered voters in the U.S. Otherwise, we wouldn't even really need to hold elections because we would just know who the preferred candidate is and we'd be done. Sampling helps you to make predictions about a population which otherwise would be kind of hard to you're never going to get the exact statistics related to a population, presumably. Sometimes you do, and usually there'll be a slightly different calculation for some of these descriptive statistics we're going to look at if you're talking about the population versus the sample. So we'll make some of those distinctions. We also use different symbols to show, for instance, the average for a population, the average for a sample. But there's one thing I want to make, a couple points I want to make about sampling that are very important. Number one, when you're taking a sample and you're using the sample to make predictions about a population, it's very key that you have a representative sample. And this is easier said than done. You want to be able to make predictions about the population, and so therefore your sample has to be a good reflection of the population. You can't have it skewed one way. If you're making political phone calls and you only call people during the day on weekdays, because that's when your call center is open, you're going to have a problem, because what you're going to get is a lot of people who are home on weekdays, not at work, or working from home, and they may be different, politically speaking, than the people who are working. So representative sample is really key. The other issue is having a large enough sample to make a prediction. If you go into Times Square and you measure 3 people, and you might get a very different perception of what the height is of the U.S. population than if you measure 1,000. If you measure 1,000, you're going to be, fairly close, depending on how representative you think the population in Times Square is, which is debatable. But if you only measure 3 people, you might measure 3 people who are all over 6'2". It's not entirely likely, but it's possible. If you just go up to the first 3 people you see, and they just happen to be 3 tall cousins, you might say, gee, I think the average population, average height of the population in the U.S. is 6'3". That's not the case. So having a large enough sample to make predictions, and the larger your sample, as long as it is representative, the more accurate you will be in making predictions about the population. Okay, so now let's get into the statistics themselves. Well, first we have mean, which is another word for average, median, and mode. I am assuming you are already familiar with these terms, so I'm only going to take the quickest of looks at these. First off, I want to make a distinction here. we have two symbols to designate mean, and mean, this is going to come up all the time. One when you're talking about population, and one when you're talking about a sample mean. And so this here, this is population. And this is sample. And throughout this video, I'm going to show you symbols that designate other statistics, descriptive statistics as well, related to population and samples. I'm going to write the population symbol on top and the sample symbol beneath it. Okay, mean, median, and mode. Mean is the average. You all know how to calculate this. You just take all of the you take all of the results, add them up, divide by the number of results. Median is the, if you took all the results and ordered them you put them in order, say from smallest to largest. The median is going to be the result that was exactly in the middle. And of course, if you have an even number of results, then what you're going to have is 2, and you're going to average those 2 that are in the middle, and that's going to give you your median. Mode is just the result that comes up most frequently. All right, so moving on, because I assume you're fairly familiar with that. Related to median, so related to median are some other concepts, including percentile and quartiles. Now, in statistics, when we refer to, you can talk about percents, which is a completely different concept, and then percentiles when you're talking about, like, say, a sample. And a percentile means the percentage that fall below that number. If you, like with the median, if you took all the results and lined them up from smallest to largest, you could take, say, and you say the 5th percentile. The 5th percentile is the 5th percentile from the bottom, meaning a value such that 5% of all your results are smaller than that result. So if you scored in the 99th percentile on your SAT, that would mean that 99% of people scored below you. That would be very good. Congratulations. Quartiles work a little bit similarly. So quartiles, basically, you have quartiles at the 25th, 50th, and 75th percentile. That breaks down all of the results into 4. So from 0 to 25, essentially 25 to 50, 50 to 75, and then 75 to the largest result. That's going to be your quartiles, and so these are all kind of related concepts. The median is just the one is essentially the median is essentially the 50th percentile, and the quartiles are the 25th, the 50th, and the 75th. And oftentimes we talk about interquartile range. I guess you could say quartiles are often defined in statistics as the 25th and the 75th percentile, and interquartile range means from all the results between the 25th and the 75th percentile. That oftentimes you'll see this actually with admissions for colleges. They'll publish their SAT range as the quartiles, so as their interquartile range. So they'll say, the bottom quartile that we admit is at 600, and our interquartile range between our bottom 25th percentile and our 75th percentile is between 600 and 700 on the math portion of the SAT, for instance. So that's called the interquartile range, and of course it represents half the results. When you go between the 25th percentile and the 75th percentile, that is half the results. All right, so enough with mean, median, mode, percentile, quartiles. I want to introduce one other term that many of you may not be familiar with. It's called the geometric mean. Sorry I'm so haphazard, sort of all over the page, but the geometric mean is used to calculate growth rates over time. And so, let me just give you the calculation that you do here. It is, I won't use a lot of symbols. It's the product of n numbers to the 1 over n as the exponent minus 1. That doesn't make a lot of sense, I know, but let's use an example here to to walk you through it. Let's say you want to double, you're running a sales department and you want to know what, you want to double your sales growth within 5 years. And you need to know, okay, well, if I want to double my sales growth in 5 years, what percentage increase do I need every single year in order to get to that rate of doubling in 5 years? Now, maybe some of you are tempted to say, well, doubling is a 100% increase in 5 years, so I need to increase my sales by 20% each year. But you would be wrong. You don't need to increase your sales by that much. And the reason is because you're not taking into account compounding. So if you increase your sales by 20% in year one, then your sales, and let's say they started out at $100,000. Now they're at $120,000. And so now if you take another percentage increase, let's say another 20% increase, you're not just counting the original 100,000 that your sales started out at, you're counting the additional 20%. So it's going to be less than 100% divided by 5. It's going to be a smaller percentage growth year on year because of compounding. And so what we would actually do is we would say, where's my pen? Okay. Doubling is, essentially we have a factor of 2 here. So the product of all of our yearly growth is going to be 2, right? We took our percentage growth from year 1 times our percentage growth from year 2 times our percentage growth from year 3, 4, 5. You multiply all those together, you're going to get 2. That's the whole concept of doubling our sales growth. So the product of our n numbers, this is 2. And we have 5 years, 5 increases to growth, so that's 1 over 5 minus 1. And if you do that calculation, actually I don't have getting a little bit ahead of myself here. If you do that calculation, we say 2 to the 1 divided by 1/5 power minus 1. I forgot to add an equal sign because I'm a total rookie. The annual growth rate that we're going to need year to year is about 15%, a little bit less than 15%, but if I was that sales manager, I would be conservative and say, we need to hit 15% in order to double our sales volume in 2 years. So that's geometric mean for you. You may not see it a whole lot, but keep in mind, this is what you're going to use when you're talking about growth rates over time, is geometric mean. All right, now on to an interesting topic. And this is something that comes up all over the place in statistics, or a couple of interesting topics. We're going to talk about variance and standard deviation. All right, did not write this super well, but variance and standard deviation come up all over the place in statistics. They're super important. Really, you're going to mostly talk about standard deviation because it's an easier term, it's an easier number to deal with and conceptualize. But you derive standard deviation from variance, so they're both important. The symbols for each, variance is usually represented for a population as this. And the standard deviation for a population is represented as the same thing without the exponent. That's because standard deviation is just the square root of variance. So I'm going to show you how to calculate variance, and then to get standard deviation, you're just going to take the square root of that. So it's pretty straightforward. And for a sample instead of a population, it's s squared for variance and just s for standard deviation. So the s for standard deviation, this is what you're going to see most often when you're talking about standard deviation of a sample, is just going to be s, and variance is just s squared because standard deviation is the square root of the variance. Let's look at an example. I think that'll be a lot more illustrative. Here I have the quiz scores of a class of 20 students. And I want to know what is the standard deviation. We'll talk about what it means in a moment, but basically that's what I'm interested in getting. I'm interested in getting the standard deviation of all the students in this class who took this quiz. Now, in this case, we're going to treat these quiz scores as, in this class, as the population. I'm not interested in conjecturing how these quiz scores might translate to, all the students at the school if they took the quiz. In that case, I'd treat it like a sample. But in this case, all I care about, I am just the teacher of this class. This is the only time I'm issuing this test, and I just want to know what the standard deviation is so I can sort of figure out, where people stand in the class. So we're going to treat this as a population. You would do a slightly different, very slightly different calculation if you were looking at standard deviation for a sample size, but we're not going to get into all that now. You're going to see that more later on. So first thing we have to do to calculate, we're going to start off by calculating variance, and we're going to use variance to get to standard deviation. And so for the first thing we need to do is calculate the average of these quiz scores. And you all know we can get that by adding up all these scores, there are 20 of them, and then dividing by 20. The other thing you can do in Excel is just say equals average. Same exact thing. We'll do it both ways, just so you all can see how useful Excel is. But now let's look at variance. To get variance, what you do is you take the difference between each individual value, the difference between that individual value and the mean of all the values, square it, add them all up, and then divide by n, which is the number of results that you have. So let's think about that again. You're going to take each individual value, the difference between that individual value and the mean of all the values. So let's start writing this out. Equals this minus the mean. Square that difference. And then we have to add them all up. So let's, oops, did something wrong here. Forgot to make this an absolute reference. So now we have all the differences between the individual values and the mean squared. That's what this shows us. If we add them all up, actually I've got to add them all up and then divide by the number, 20 of them, and that is our variance, which I didn't put in the right place. Let's just use Excel to make sure to double check our work. I'm going to write equals variance. I'm going to treat this like a population, as I said. Variance of all those quiz scores. Lovely. That's actually the same value. We just had one more decimal place. Beautiful. And the standard deviation is just going to be the variance. It's the square root of the variance. And again, to use Excel to double check ourselves, I'm going to write equals square root, equals standard deviation of the population. Grab those numbers. These look like the same numbers. I'm going to guess they are, but lovely. Okay, so that's how you calculate standard deviation and variance, but what the heck does that all mean? Well, like I said, we're mostly going to talk about standard deviation. Standard deviation is a great concept because it tells you how much variation there is in your sample or your population in this case. So it says, I don't know why I moved everything over one. Let's put it back here. I got out of hand. Okay, so if our standard deviation is roughly 13 and our average is 76.25, we'll call it 76, that tells me that a certain distribution tells me how far, how much range there is in my results. And the key here, and we're going to get to this much more later on, so don't worry about if this is kind of confusing, is that for most sets of numbers, most, especially when you're talking about something like a quiz results, what's going to happen is you can predict pretty accurately. You can say, look, everything between minus one standard deviation below the mean and one standard deviation above the mean, that's going to be about 68% of my results. If I take 2 standard deviations in either direction, that's going to be like 95% of my results. And if I take 3 standard deviations below and above the mean, that's like almost everything. Pretty much everything's going to fall within 3 standard deviations. So this can help a student interpret their score. It helps them say, well, gee, you know, if I scored, you know, like 89, so that's about 1 standard deviation above the mean. That tells them something. If they know that 68% of the scores are within 1 standard deviation, this is a little bit of a leap, but okay, bear with me here. That means that about 84% are going to have fallen below a score of 89. That's, you know, the outliers on that 68% is going to be 16% above 1 standard deviation and 16% below 1 standard deviation. So someone scoring exactly 1 standard deviation above is going to be at about the 84th percentile. Now, okay, if this doesn't make a ton of sense to you right now, don't worry about it. We're going to go into this very extensively, but it tells you 2 things. Where, you know, how much range, how much variation there is in the results, the standard deviation tells you that. And you can look at one result, and based on the number of standard deviations they are from the mean, it's really going to tell you about sort of where they stand as far as percentiles go. So for instance, if the average height of men in the US is like 71 inches, and the standard deviation is, I don't know, 3 inches, and you're a 5'8" man, meaning you are 68 inches tall, that's you figure, okay, I'm about 1 standard deviation below the mean. And actually, there's another term that I'm going to put in here as well called a z-score. And right now, we're just going to define it as the number of standard deviations from the mean. Not from the mean, from the mean. All right, so like I said, you're going to see lots of z-scores in the future. Last concept I wanted to address with regards to standard deviation, z-scores, and all that is the coefficient of variation. I've got to make myself a little bit of room here so I can address that. Coefficient of variation. And this is a term that you use to describe a sample set, for instance, that helps you determine sort of how much variation there is within that sample. And so what it is it's, if we're talking about a sample here, it's going to be the sample standard deviation over the mean, sample mean, times 100%, because usually it's expressed as a percentage. So it's basically how large of a percentage is the standard deviation of the mean. So, you know, larger means there's more variability in the data. And if we're talking about populations, of course, it's going to be just different symbols, but exact same concept. So this is sample. Not a great job writing that. And this is the population. All right, let's move on now to the idea of a weighted average. And this is something that I think a lot of you are going to be pretty familiar with. So I just want to set it up because it leads us into another very important concept called expected value. So when you're talking about a weighted average, I think a lot of you have done this before. When you have data where, you know, there's multiple points that have different values, you can't just take, you may not just be able to take all the different points, add them up, and divide by, you know, their total. You may have to say, okay, well, some of these occur more frequently than others, so we have to weight that when we're calculating the mean. And so let's look at a weighted average. The example I've got here is calculating your GPA, and I bet a lot of you have done this in the past. We can't, if these are the grades that you've earned throughout your, I don't know, time as an undergraduate, let's say, you never actually got anything below a B minus, So this is not the entire range of grades. And you never got an A+. But these are the grades that you have earned. And here's the grade point average that's associated with each of them. You can't just take these grade point averages, add them up, and then divide by 5, because you may have gotten some of these grades more than others. In fact, that's what we see here. In fact, we see that the mode is for you to have gotten a B+. You got B+ more than anything else. But you seem to have you got more A's than you say you got B's and B minuses. So we have to take this into account. So the way you do this calculation is you multiply each value by its frequency for all the values. You add them all up, the values times their frequencies, and then you have to divide by the total number of values, which is 21. Not the total number of values, it's the total number of instances, which is. So this is your GPA. It's just somewhere in the middle between an A- and a B+. So 3.48 is your GPA, and so this is how you do a weighted average. You have to take the value times the frequency, add up all of those, then divide by the total number. All right, this is important because it's going to help us do something called expected value. Expected value is a term that's going to come up a lot in statistics. It comes up all in finance and econ as well. It's this idea of doing a weighted average, but we're talking about probabilities and percentage probabilities. You can do this with fractional probabilities as well. We're talking about probabilities, and so it gives us sort of an average of what we would expect to come out with in a specific scenario. So let's take a look at this example here. Using what you know about weighted averages, I'd actually like you to pause this video and perform this calculation yourself and determine which investment opportunity you would prefer. Okay, go. Hopefully you've come up with an answer here, and we're going to work through it as well. So using the same principle as we had with a weighted average, what we're going to do with expected value is we have to multiply the percentage chance of something occurring with the value that you would get from that instance occurring. So here we have two investment opportunities. The first one gives us a 10% chance to earn $2,000, so we're going to call this a value of $200 because it's 10% times 2,000. A 20% chance to earn $100, so that's going to be equal to $20. A 30% chance to earn $10, and so that's going to be equal to $3. And a 40% chance to earn $0, and that is equal to $0. Now we have to add all this up, and so we add it all up, we get $223. That's the value of investment opportunity A. And we don't have to divide by anything because since we were talking about percentage probabilities, they're going to add up to 1 anyhow, so we don't have to divide by 1. That's unneeded. All right, so let's look at opportunity B. We have a 25% chance to earn $400. That's going to be worth $100 to us. By the way, I don't know how this turns out. I didn't do the calculations yet, so it'll be a surprise to me. 25% chance to earn $300. That's going to be equal to $75 because we multiply 25 times 300. A 25% chance to earn $200 is going to be $50. It looks like we have a winner. And a 25% chance to earn $100 is going to be equal to 25. So add all that up and we get $250. Which investment opportunity would you prefer? Aside from risk and all that, the chance to score big, you would probably prefer opportunity B because it is a higher expected value. Meaning, we don't know what's going to occur, but on average, we would expect it to return about $250. We would expect opportunity A to return, on average, about $223. Therefore, investment opportunity B seems like a better bet for us. So this is our expected value of opportunity B is $250. All right, that covers our descriptive statistics. I promise we'll do more fun things with probability that aren't just so many definitions in the next video.